First mathematical topic of the course is the Markowitz mean-variance model. A little bit of introduction to the Markowitz model. Well, Harry Markowitz wrote a PhD back in that he finished back in 1952, which dealt with well, asset allocation using an optimization model that I'm going to present to you in a minute. But essentially, then he spent the next 40 years following up on his PhD thesis, doing all kinds of further analysis, which brought us to this idea of the CAP-M, capital asset pricing model. Some of you from the introductory course might have heard about that. And for that, he received actually a Nobel Prize back in 1992. So it kind of took 40 years from the PhD to get the Nobel Prize. And kind of the funny anecdote is that when in 1952 he had finalized his PhD on this topic, presenting his model, he was kind of unsure whether or not he had done enough to go through his PhD. And the examiners were not quite sure if that was because he was from the economical faculty, and what he had done was not really economy. And then there was one of the examiners who had to examine him at his PhD defense was a well-known mathematician who really thought that his mathematical contribution was not really deep enough, right? So he was coming from the Department of Economics, University of Chicago, and he didn't have essentially any economical contributions, and the mathematics were not deep enough. But anyway, they kind of let him pass through. But then we'll kind of later found out that he had laid the groundwork for what we call kind of modern asset allocation theory, right? So that's and then that's the thing that finally he got his Nobel Prize for in 1992. When I go through the model, you will find out that this is a pretty simple model. So per se, it's not. I mean, you will see that mathematical sophistication is not very high, and the economical contribution probably not very high either. But sometimes simple models are actually more useful than more complicated models. And what is more important is a frame of mind, as a frame of thinking in asset allocation using optimization techniques that he introduced to the world, that many researchers since 1952 have been building on top of. Right? So some of the other models that you're going to see in this course, they are all extensions to that way of thinking. Even though the models might look very different, still they are all building on top of the works of Harry Markowitz from 1952. So in that sense, you could say that Harry Markowitz was the founder of optimization in finance, introducing a formal optimization model tackling a classical financial asset allocation problem. All right? So let's go through what that model is about. And before that, we need a couple of introductions to the input parameters of the Markowitz model. Essentially, there are two simple inputs to the Markowitz model. The purpose of Markowitz model, for one thing, is to find out what is the optimal allocation to a set of assets if you want to invest your money, right? And for that, you need to have an idea of expected returns of the individual assets, and then you need to know what is the covariance matrix of the returns of these assets. Right, so these are the two inputs. I'll get back to how they come together. But first, let's just look into the how they are defined individually. So we are looking into a set of assets. We call them I, going from 1 to n, set of assets or instruments. So if you will, I will interchangeably call them assets or actives or instruments. Could be stocks or bonds or in mutual funds, financial products that you can invest in. Right? Those are the instruments. So we have n instruments, and then we have a time series, time steps, for which we have prices for these instruments. So the only thing we have is historical prices of these financial instruments, right? And the way we calculate return is that we say the price today minus the price yesterday divided by the price yesterday. This is the return calculated in discrete time steps, right? So let's keep it to discrete time steps for now and probably for the entirety of this course. That will suffice. And then the way you average that, you say, well, if I have 10 different time points, then I get 9 returns, and then I multiply. So I just sum these 9 returns and divide it by the number of returns that I have. So I have time 1, time 2, time 3, let's say, to time 10. So and I have a price at time 1 and a price at time 2, right? So the first return that I get is the return at time 2, which is then my return. Sorry, is my price at time 2 minus price at time 1 divided by price at time 1, right? So that's simple calculation of the return. And you see if I have 10 points, then I get 10 observations, historical steps. Then I get 9 returns. That's why I divide by t minus 1, t being the number of observations of prices that I had, right? So pretty simple, basic math, just for calculating the returns from historically observed prices, right? Now the question comes later whether historical data would be a good representation for expected returns of the future. It's a very good question. We are not going to address it in this lecture. I'm going to get back to that later towards the end of the course. We'll discuss this a little bit, how we can we have other expectations. But for today and for the project work that you will be doing, we can just look into historical observations of prices, and based on that you can have an expectation of, well, this is going to be my expected return in the long run as well. Right, and then we have the covariance matrix. So the covariance matrix, which is used as a measure of risk in the Markowitz setting, where the covariance matrix is defined as like that. So you have the average returns for the asset I, and covariance says something about how the prices of how the returns of two different assets are correlating with each other, covariating with each other, right? So if you have, just to get an understanding of how this formula works, then let's say if you have asset 1 and asset 2, mu I and mu j for being 2 different assets, then we are observing, the returns from the second observation to the last one. Then so let's say if at the same time you have a return for asset 1 which is greater than its average, and at the same time you have the return of asset 2 being greater than its average for all different time steps. So if either the returns of asset 1 and 2 are higher than their average, or they are lower than their average, would that give a positive or negative correlation or covariance? Yeah. Right, because exactly. So that's the point. So if both of them are higher, if they're at the same time higher or lower, if they're higher or lower, you would then get either both positive or both negative, but you multiply the negatives, then you get the positive. So that is the definition of positive correlation, right? But if at the times where the one is over its average, the other is under its average, then they have different signs, the one positive, the other negative, then you get a lot of negative. And that was essentially the core contribution of Markowitz, right? And then you could understand why the mathematics professor back in 1952 thought that contribution was not deep enough mathematically, right? Because I just explained it to you in less than 1 minute, and then all of you can do a PhD if you came up with something as simple as that. But of course, it would be as useful as that. Probably that would go through both for a PhD and maybe also a Nobel Prize. Who knows, right? But that's essentially, that was the core contribution of the Markowitz model, coming up with the covariance matrix as a measure of risk, because the thinking was that, well, we can, if we go back historically, and have an idea into whether the assets are, they are correlating positively or negatively to each other, and then we form portfolios of assets which try to reduce the total, what they call portfolio variance, that he also defined. We'll get back to that in a minute. Then we introduce the idea of diversification based on portfolio variance, and then that's gonna remove financial risk to a certain extent from what's called idiosyncratic financial risk from our portfolio. All right, so all the risk that can be removed then could be removed by using a method like this, given some assumptions. I'll get back to that as well. And of course, then we have a special case of a covariance is the variance, where you have the covariance of the same asset with itself, right? And that would obviously be always a positive number. Right, so here's the Markowitz model. So that was the model he presented back in 1952, where he essentially is saying that we want to maximize that objective function. And that objective function that you see on the top, you're maximizing two different terms. So the first term, summing mu times x, summing them over I. That is, what does it represent? Return. Yes, portfolio return, right? So this is kind of the portfolio average return, right? The average or expected return of the portfolio. We want to maximize that. And then before getting to the second term, if we are maximizing to negative of something, then in a sense we are doing what? Then we are minimizing, right? So this is a bi-objective optimization model where you are maximizing return while at the same time minimizing risk, right? And the way you do that is by putting some weights, because if you don't put any weights, that means that we have equal weights on both of them. But if you're putting weights called lambda in this case, then you can change the lambdas, and then you don't get one solution, but you get a frontier of solutions, which is called an efficient frontier, right? So by changing values of lambda, you can put different weights on whether you want to maximize risk to a higher degree than maximizing return to a higher degree than minimizing risk. And for different values of lambda, you get different values, which would look something like this. And by the way, the convention is that you have the risk here, and in the Markowitz term, the risk is defined as the sum over I and j of the weight on asset I multiplied by the covariance matrix of I and j times the weight on j, summing that up. So that term is called portfolio variance. So the risk in the Markowitz setting is portfolio variance. And here you have the expected return. Right? And well, in our case for now, we are just taking expected return as the average historical return, but then there are other ways. You can use the machine learning techniques, or you can use economic kind of forecasting models or what have you to come up with other and better estimates of future expected return. None of them, unfortunately, work all that well. So at the end of the day, if you're using just historical returns, or if you're using something more advanced, you can't be quite sure that you can do it better than just looking into historical expected returns. Whereas the measure of risk is normally more robust, right? So one of the ideas around using optimization methods is to focus more on risk management rather than trying to second guess the future. Here is about second guessing the future. At the end of the day, if I knew that one asset is going to have a higher expected return than the other, what would be the rational thing to do in the long run if I was a long-term investor? Or let's even look at the model. So let's say if the value of lambda is 0, what happens with lambda 0? The second term disappears, right? So for lambda 0, I would be just maximizing expected return. Then can anybody tell me what would the model find if I'm just maximizing expected return? What is the nature of the solution of that model. Yeah.
Highest return, of course.
Right, the highest expected return, right? So you put 100% of the money in the one asset which you guess has the highest expected return, right? So that would be the natural way of thinking if we had good methods, good models to tell us exactly what asset is going to have the highest expected return in the future. Then why bother to take a course like this? Then you can just put all your money on that one. So you maybe want to take a course which doesn't deal with risk management, looking into this term, but only focus on finding good estimates for future return. But then you can think of the problem with that thinking. Because if such methods were there, would you think that somebody actually would take advantage of them? Probably yes. And if people start trying to take advantage of those methods, what would happen with the performance of those methods?
They won't be always the highest one.
Right. So because your actions always change the output. That's what we call in financial markets or in economy in general, that our actions actually have an impact on the kind of the subject matters that we are actually working with. So these kind of financial, in finance we call this, the price of financial assets is called an endogenous parameter. So you have the difference between endogenous and exogenous. Like an exogenous variable could be the wind, like how the wind is blowing. The wind doesn't care, if you have a model at DTU Compute, if come up with a model which is going to guess how strong the wind is going to blow, in which direction the wind is going to blow next week. The wind is going to blow the way the wind wants to blow, right? No matter what your actions are, the way you want to put the turbines or the windmills to take advantage of the wind, or plan for your electricity production, for example, of that week, right? So that's the blowing of the wind is an exogenous variable to your model, whereas the prices in financial markets are endogenous to your models. So that's why it's kind of a contradiction in term to have a good model which could always guess the future expected returns. That said, there are people who are trying to do that, and there are small, short periods of time that you might be capturing some signals and act on that, but that's not what we're focusing on this course. The main focus would be working with risk management when it comes to asset allocation. Right? Any questions in understanding? Oh, I didn't draw the efficient frontier. So the efficient frontier looks something like this. So this point would be the one where you have a lot of focus on risk. You have very little risk, and normally you have, that's essentially, by the way the financial markets work, the less risk you want to accept, the less return you should expect as well. And this point is the one where you are getting maximum risk and maximum return. And normally you see this shape that it's not a linear shape. So you are the more risk you are taking, you are not necessarily taking excess return corresponding to that. In linear, it would be actually falling down. So after some point, probably you're not really getting much returns from the extra excess risk that you're taking. So this is the usual shape of this curve. Any questions to the Markowitz model or the way risk and return were defined? It's quite clear. Yeah, was one question?
Why is it always one?
That's a good question. Essentially, this two. Let's just spend a minute on that as well. So sum of x is equal 1. That means that you have to invest 100% of your money. So in this case, 1 represents all your money, right? And x greater than 0 means that we have to have a long position in all these stocks. That's not actually a requirement of the Markowitz model as he introduced it back in 1952, but we're going to get actually back to that, because adding this constraint makes solving this model a bit more difficult. So he didn't, when Markowitz solved the original problem, it looked like this. So actually the x's then could be both positive and negative. And you might have been presented to that version of it also introductory course. But essentially, having x is greater than 0 means that no short selling is allowed. But we're going to talk about short selling next week, and you will, you can ask questions on that. But for now, it means we have to spend all the money on buying the stocks, and we are not allowed to short sell. Any other questions? Right. Otherwise, I'm done for the lecture part. We're going to take a break of let's say until 10 past 2, and then we're back for the exercises.